Okay, welcome everyone to today's live interaction session. Wait, let me share my screen first. Okay, so welcome everyone for today's last live interaction session on MATLAB-based programming lab in chemical engineering. In today's session, for uh, all rest of the 2 hours, what we will be doing, we'll be revising whatever we have learned till now. Okay, so just small introduction of mine. Myself, Prasil Kapadia. I have completed my BTech in chemical engineering from SVNIT Surat in 2019. After that, I worked in Reliance Industries Limited at Jamnagar for a year. Then further, I completed my masters from IIT Kharagpur. During my masters, I learned a similar course to this from Professor Parag Deshpande. Currently, I am pursuing my PhD from IIT Bombay. This is my personal web page, LinkedIn ID, and YouTube where you can connect with me. And this is the YouTube channel where all these videos are getting uploaded. Yes. So let's start it. So let's first see what we have studied till now. So first for the first few lectures, what we did, we learned how what we can do with MATLAB. We wrote very small codes just to learn how one can write a code. After that, we started with our actual systems. First, we learned nonlinear equations, solving methods for nonlinear equations. And if you remember, what did we learn? We learned fzero, MATLAB inbuilt command, and fsolve. F0 and we learned F0 and fsolve, MATLAB inbuilt command. And when we are having cubic kind of equation, we can also use roots command. Polynomial kind of equation, then also we can use roots command to solve the equation. Further, we moved ahead with linear equations, and for linear equations, we used linsolve command, MATLAB linsolve command available to solve. Further, we learned how to determine rank determinant of the matrix, eigenvalues, eigenvectors, all these things we learned in linear equations part. Then we moved ahead with initial value ordinary differential equation. And for initial value ordinary differential equation, we learned various methods to solve it, like Euler method, RK2 method, RK4 method. And then we learned some MATLAB solvers like ODE23, correct? ODE23 we learned, ODE45 we learned. These MATLAB inbuilt command we learned. Then we moved ahead with the boundary value problems. So boundary value problems, we used BVP, 4C, MATLAB inbuilt command to solve that boundary value problem and to write down the boundary conditions. We used BVP init, MATLAB inbuilt command. Further, we solved partial differential equations, and there we learned PDEpe, MATLAB inbuilt tool to solve these partial differential equations. We further used PDEToolbox, where we solved two kind of problems of heat transfer. Then further, we looked ahead with optimization. For optimization, we used fminsearch MATLAB inbuilt command, and fmincon command. This also we will have a look today. And further, for data fitting, we learned about polyfit MATLAB inbuilt command and polyfit MATLAB inbuilt and lsqcurvefit. Sorry, not LQ. It's lsqcurvefit MATLAB inbuilt command to fit our data. So in today's session, we are going to take one I guess 2 to 3 examples to solve each kind of problem, and we will revise what we have looked till now. I guess this will be useful for your final examination. Okay, so I hope we are all set, so we can move ahead. So let's start with just a minute. I don't know why it's yeah. So let's start with today's session. With first, we will be learning how to solve. We will be learning or we will be revising how to solve nonlinear equations. So let's read. I will read out the problem. The problem statement says that the adiabatic flame temperature T in Kelvin for burning methanol with 100% excess air in furnace is given by this following expression. The adiabatic flame temperature in is the upper bound of the temperature that is reached by the actual processes and serves as an important parameter for furnace design. So here it's written upper bound. Find the adiabatic flame temperature in Kelvin. Correct to two figures after decimal using the fsolve in MATLAB. So let's first uh, search about fsolve and let's try to revise what we learned about fsolve command. So the syntax for fsolve is really simple. The syntax for fsolve command is really simple. We just need to write x is equal to fsolve function comma x0. So if this is the example, then my function is this equation and x0 is some initial guess that I need to give. So let's solve this problem in MATLAB. So how can I do it? So first I will write clear all. You can also mention close all to close all the prevailing, let's say graphs are open or something. Okay. Okay. So what is my equation? My equation is equal to F is equal to the equation that this is the function of temperature. So F is equal to at the rate of T, something that I want to solve for. T, what is the equation? 1.3 into 10 raised to minus 8 T cube. So 1.3 E minus 8. So this means 1.3 into 10 raised to minus 8 into T raised to 3 cube plus it is 4.9 into 10 raised to minus 5 T square. 4.9 into 10 raised to minus 5. So I can write 4.9 E minus 5 into T square, then 0.47 T, 0.47 into T minus 681.7 minus 681.7. So this is my function. I have written down it. So my equation is ready. So what do I need to now? What is the syntax? The solution, let's say this is my solution. So I am writing as T is equal to fsolve, then function, comma, initial guess. So what should we give? Let's say my initial guess is 298.15 Kelvin. And if I'm not putting semicolon here, so it will display the result here only. So when I run it, okay, so I'm getting some answer of 1.2381 into 10 raised to 3. So that is 1238.10 Kelvin. So if I keep here format long in G, so I guess we will get this whole its format, not yeah. So if we do this, so see you can see it like this. So it is 1238.1138 Kelvin. So this is how we can solve it using fsolve. If I use let's say f0. So what do I need to do? I just need to write f0. I guess f0 will work. So f0 is also giving me same answer. If we use roots command, so in roots command, what do we need? We need only coefficient of polynomial equation. Okay, so let's just revise it very quickly. See, represent roots of only polynomial. So it is p comma x. Okay, so I just need to see, this is what we can do. I can write t is equal to roots of, let's say I'm just first defining one matrix, let's say A, that is coefficient matrix. So first coefficient is this one, 1.3 into 10 raised to minus 8 into t cube. Then my second coefficient is 4.9 into 10 raised to minus 5 t square. So I just need to give coefficient. Then this one is 0.47. And my last one is minus 681.7. And if I use roots common, so I can write roots of A. So I provide this, I will have three solutions. Okay, so which are these three solutions? Two are negative and equal, and one is 1238.11. So our correct answer is this. So roots we can only use when we are having some kind of polynomial. So I hope it is you all remember how we did this. So now let's move it with the next problem of nonlinear equations category. The question is, for turbulent flow through pipes, the friction factor is a function of Reynolds number, the relative roughness phi. The Colebrook correlation is given by 1 upon square root of f is equal to minus 0.8686 ln phi divided by 3.7 plus 2.51 divided by Reynolds number into square root of f. Using the suitable MATLAB solver and considering phi is equal to 2 into 10 raised to minus 3 and Reynolds number is equal to 5 into 10 raised to 5, compute the friction factor. So here it's written suitable solver. So can we use roots solver? No, we can't use roots because this is not a polynomial equation. So we can either use fzero or fsolve command. So let's solve this problem. So this problem is we have to solve for friction factor f. Okay, so I will clear this thing till here. Okay, so my function f is equal to, okay, let's not write here. I'm writing fun is equal to at the rate of, we want to solve it for friction factor f. Okay, be really careful while writing this equation. It is 1 upon square root of f. First term, 1 divided by sqrt square root of f. This is my first term. Then my second term is plus, okay, I'm using two brackets here. Just I will first close this bracket. Okay, then I will have plus 0.8686 0.8686 into, okay, ln. So in MATLAB, we don't have ln, we have log only. So if I write just log, so see log 10, meaning if I want to have base 10, then I need to write log 10. And if it's natural logarithm, so I just need to mention log. So log e divided by 3.7. So my first term, let's say I'm writing phi divided by 3.7. So I need to define the value of phi plus 2.51 divided by RE into square root of f. So I will use one more bracket, RE into SQRT of f. So this bracket is closed, this is closed. This whole thing is in log, that we need to be careful. So that is also closed. This is closed and this is also closed. Yeah. No, we have not closed one more bracket. Okay. So this is how we have written the equation. Be really careful while writing this. Okay, so we are given some input that phi is equal to 2 into 10 raised to minus 3. So I will write phi is equal to 2 into 10 raised to minus 3. Correct? Then my second input is RE is equal to 5 into 10 raised to 5. So RE is equal to 5 into 10 raised to 5, 5e5. And this is my function I have written. So I just have to use okay, I'm sorry guys. So where were we? Yeah. So this was the equation. Yeah. So we have written the equation. Now what do I need to use? I need to use one suitable MATLAB solver. So let's see, I'm using f is equal to f0 of function, comma initial guess. So what should we give some initial guess? Let's say I'm giving 1. I don't know if it will work or not. Let's give 1. So when I do it, it's not working with 1. So let me give something 0.5. Okay, I guess f0 is not working. So let's move it with fsolve and zero point 0.5. So see, fsolve is giving us the answer of 0.02378. So what is asked to us? Yeah, we just have to tell the answer. So it is 0.02378. So if let's say if I'm using 1 also, it will give me the solution. See, it is giving the same answer. It is like f0 is not applicable here. So this is how we can solve complex problem using complex nonlinear equations using fsolve command. Let's move ahead with the next problem. So here, what is the difference? Find a solution of the system of nonlinear equations to find the intersection of two circles with the initial guess of 0.35 and 0.6, where equation is x1 minus 2 whole square plus x2 minus 2 whole square is equal to 9, and x1 plus 3 whole square plus x2 plus 1 whole square is equal to 9. So what is this? These are two coupled equation. So now what we will be doing? We will be solving coupled equation. So let's do that. So for coupled equation, I can write, let's say f is equal to at the rate of x. Okay. Now I will be first defining my first equation, x1 minus 2 whole square. So I will not write x1, I will write x of 1 minus 2, and this whole term is raised to 2 plus x2 minus 2 whole square plus x1 minus 2 and x2 also minus 2. X of 2 minus 2. Yeah, I guess this is not needed. Whole square minus 9. So this is my first equation. Correct. Now I will write down my second equation. That is x of 1 plus 3 whole square. So x of 1 plus 3, that is whole square. 3 whole square plus x of 2 plus 1 whole square plus x of 2 plus 1 whole square minus 9. So this is my second equation. Okay. So now what do I need to give? I need to give, I just need to solve it. So let's say x is equal to f solve my function, that is f. And what is initial guess told to us? That is 0.35, 0.6. So that is 0.35, 0.6. Okay. So let's run it and see what are the solutions that we are getting. Okay. Okay, let's do one thing. Let's write it like this. So see, my first solution is minus 0.02378. 0.1362 and x of 2 is minus 0.1063. So let's see minus 0.1362 and minus 0.1063. So this is my solution. Correct. So this is what we all learned about nonlinear equation. Let's revise it once again. So what did we learn in nonlinear equation? We first learned how to write a function or how to write down an equation. Then we solved single equations using fzero and fsolve command. And when we are having polynomial kind of equation, we can also use roots MATLAB inbuilt command. So these three things we learned. Then further we checked about how to solve system of equations like coupled equation. These two are coupled equation and we need to solve them simultaneously. So this is what we also learned in nonlinear equation and we solved it using fsolve MATLAB command. Okay, so this is all about nonlinear equations. Okay, so now, okay, before moving ahead, what are the examples, chemical engineering examples that we have learned in nonlinear? Those are in nature of nonlinear kind of equations. So one of the best examples for this is this we have already seen from here, this friction factor kind of equation that is nonlinear in nature. Then one other example is cubic equation of state, V cube av cube plus bv square plus cv plus d is equal to 0. This is also kind of nonlinear equation from thermodynamics. Then this kind of equations we come across through various problems. So this is what we have learned. Okay, let's move ahead with linear equations. So for linear equations, okay, so what we have learned linsolve MATLAB inbuilt command. Let's have a look at linsolve. Okay, so let's read out what linsolve says. So see, x is equal to linsolve a comma b solves the linear equation ax is equal to b using one of these methods. When A is a square matrix, linsolve uses LU factorization with partial pivoting, and for all other cases where it's not a square matrix, linsolve uses QR factorization with column pivoting. Okay, so let's try to solve this. Solve the following set of linear equations and report the value of x1 truncated to one figure after decimal. Okay. So let's write down our equation. So I will be writing here equations, whole equation, just for better understanding. Okay. So my first equation is 7x1 plus 9x2 plus x3 is equal to 6. 7x1 plus 9x2 x2 plus x3 is equal to 6. This is our first equation. Then our second equation is 6x1 plus 4x2 plus x3 is equal to 4. And my last equation is 3x1 plus 9x2 plus 3x3 is equal to 2. So here there is coefficient of 1. So what do we need to do? We need to write down our equation as ax is equal to b and we need to define our A matrix. So let's define A matrix. So what is A matrix? The first row of A matrix is 7, 9 and 1. 7, 9, 1. Then we are heading to next row. That is 6, 4, 1. So 6, 4 and 1. We are further adding to next row, that is 3, 9, 3. So it is 3, 9, 3. Okay, so this is my matrix A. Now I need to use matrix B. So matrix B is equal to, what is the first row of matrix B? That is only one element, 6. Then my next row is with 4. And my further next row is 2. Correct? So we have defined our A and B matrix. Now to solve this problem, what do I need to use? Linsolve command. So let's say x is equal to linsolve. What was the format? Linsolve of A comma B. So A comma B. Okay, and if I run this, I will get the solution. So I'm getting it as 0.611, 0.277 and minus 0.277. So what is asked to us? X1 truncated to one decimal, one figure after decimal. So my answer is point 0.6. Correct. So what is another way of solving this? So if let's say that inverse of matrix is defined. Let's say I'm finding inverse. So how can I find the inverse of a matrix? Using inv MATLAB inbuilt command. If I use inv of A, so it will give me the inverse of matrix A. If we think logically that Ax is equal to B, then what can I write? X is equal to inverse of A into B. This is what we can write. So if inverse of A exists, then what I can do? I can do inverse of A into B. So my solution can be X is equal to, if I don't want to use linsolve, then my solution can be inverse of A into B. If I do that, then again I get the same solution. So further what we can do? Further, I can also do this. X is equal to, it is not A divided by B. Correct? It is not A divided by B, but it is A backslash divided by B. So I will do this. So this will also give me the, okay. I have put semicolon, so my solution is not visible. So I will also get here the same solution, that is 0.61, 0.27 and minus 0.77. So this is how we can solve a system of linear equations. Let's take one more example to solve this. So I will read out the problem statement and let's try to solve this. The material and energy balance equations in a single effect evaporator which concentrates fruit juice are given as total material balance MF minus MP minus MV is equal to 0. Total energy balance 44.9 MF minus 65.1 MP minus 1113.7 MV is equal to minus 952 into 10 raised to 3. And solids material balance is given as 0.1 MF minus 0.55 MP is equal to 0, where MF, MP and MV represent the mass flow rates of feed, product and vapor respectively. The value of MV correct to the nearest integer is. So we are supposed to find a value of MV. Okay, so let's do the same exercise. So let's first write down the equations here, so we can understand what is the matrix. My first equation is MF 1 MF minus 1 MP 1 MP minus 1 MV is equal to 0. 1 MV is equal to 0. This is my first equation. Okay, then my second equation is 44.9 MF. 44.9 MF 44.9 MF minus 65.1 MP minus 65.1 MP. So I'm just keeping it in a good format so you understand what we are doing. Minus 1113.7 MB minus 1113.7 MB that is equal to minus 952 into 10 raised to 10 raised to 3. So that is minus 952 into 10 raised to 3. This is my second equation. And my last equation is 0.1 mf. So 0.1 mf minus 0.55 mp minus 0.55 mp. There is no mv term, so let me write it down as plus 0 mv is equal to 0. Okay, so what do I need to do now? I need to write it down as ax is equal to b. Correct? So my A matrix is 1 minus 1 minus 1, first row of the matrix. Then my second row is 44.9 minus 65.1 minus 1113.7. This is my second row. And my third row is 0.1 minus 0.55 and 0. Okay, this is my third row. Okay, so this is my A matrix. Now let's write down matrix B. So for matrix B, first row is 0. Then second row is minus 952 into 10 raised to 3. So I can write minus 952 E3. Then my third row is 0 again. Correct? So now what I can do? I can write M is equal to linsolve A comma B. So this will give me the solution. So what is the solution? So first value of M is my MF. So MF is equal to 1084.16. My second value is MP, that is 197.1096. My third value is MP, that is 886.99. So what I am asked, the value of MV, correct, to the nearest integer. So what is that integer? It is 887. So this is how we used linsolve command. If I don't want to use linsolve, then what I can do? Inverse of matrix A into B. So if I do this, I should get the same thing. And I am getting that the same thing, correct? And one more exercise that we can do is A backslash B. So this will also give me the same answer. Okay, so we revised how we solve linear kind of equations. Okay, so next question is compute the rank and determinant of the following matrix using suitable inbuilt function in MATLAB. Okay, so to calculate rank, the command is rank only, and for determinant it is det, that command. So let's do it. So I'm doing it here. So my M is equal to my first row 0.7, 0.5, 0.4, 0.7, 0.5, 0.4. Then my second row is 2, 1.8.3, 2, 1.8.3. And my third row is 0.6, 1.9, 5.6, 0.6, 1.9, 5.6. Okay, so this is my matrix M. So if I want to calculate rank, so what is that inbuilt function? That is rank only. So if I write rank of M, it will give me rank that is coming out to be 3. Okay, let's say I want to calculate determinant. So for calculating determinant, the MATLAB inbuilt function is det, det. So det of M will give me determinant that is coming out to be 2.235. Okay. Further, what I can do, I can calculate eigenvalue. So it is EIG of M. So these are the eigenvalues that I am getting. Okay. So these kind of small questions may be there in your examination. Okay. So this is all about solving linear equations. So what did we learn in linear equation? We can solve our equation in three ways. One using linsolve command. Then second is if inverse of matrix is defined, then we can use inverse of A into B. And we can also do A backslash B command to solve this kind of linear equations. So what kind of example we learned? We learned a distillation column where the material balance are linear equations, so that those equations we simultaneously solved. And further we also learned one example of heat transfer through a cylinder where we learned where we solved linear equations and we found T1 T2 T3 3 interface temperatures using this MATLAB linear equations function linsolve. Okay, so this is all about linear equations. So till now, what did we cover? We first cover nonlinear equations. For that, we used fsolve command, fzero command, and for polynomial kind of equation, we can further use roots command. And for linear equations, what did we learn? We learned linsolve command, inverse of A into B if inverse is defined, and A backslash B. Those two are same. So this is what we learned till now, or we revised till now. So now we will be solving ordinary differential equation with initial value problem. Okay. So let's try to what is initial value problem. The initial value problem is when one x is equal to 0, or let's say one time t is equal to 0. At the starting point, the value is given to us. So that is called initial value problem. The initial condition is y of 0 is equal to 0.01. What does this mean? Y of 0 is 0.01 means when x is equal to 0, my y is equal to 0.01. So the initial condition is y of 0 is equal to 0.01. Integrate up to x is equal to 0.8 and report the value of y of 0.8. So we are supposed to find the value of y at x is equal to 0.8. Truncate the answer to two decimal places. And my equation is dy by dx is equal to dy by dx plus xy divided by 1 minus x square is equal to x into square root of y. So let's solve this equation. So what can we use? We can use ODE 45 solver. So if we search about ODE 45, so see this thing. We need to write ODE function, then time span, it is t comma y, and initial guess, not initial guess, initial condition y0. So let's do this. LC. So let's first write down the equation. So how can I write it? Let's say I'm defining function here. So my function dy dx is equal to, what is the name of the function? Let's say the name of the function is ODE and that contains x comma y and n. So my differential equation is dy dx is equal to, what is that equation? X into square root of y, x into square root of y minus x into y divided by 1 minus x square. So this is my dy by dx. Okay. So this is my ordinary differential equation. Okay. So now what do I need? when I am using ODE 45 or ODE 23, we need X span and Y0. So my X span can be what, at what value of X we need the answer. We need at X is equal to 0.8. So we will start with X is equal to 0.0. We have to reach to X is equal to 0.8. Let's say I'm going in the interval of 0.1. Okay. So this is my X span. Y0 is my initial guess. So that is given as initial guess, not initial condition, that is given as 0.01. Correct? So my answer is X comma Y dy by dt. If it is dy by dt, I should have written t comma y. But as it is dy by dx, I have written x comma y is equal to ODE 45. Correct? Now, what do I need to write first? I need to write the function. So that is at the rate. I'm calling the function that is ODE. Then my x span and my y0. So this will give me the solution if I run it. So see, I am having, let me open it here. So I have values of y. Okay, so what is the question? The value of y at x is equal to 0.8. So my last entry. So whatever is my last entry of y will be my solution. So that is 0.0465. Okay, so this is how we can solve this. If I further reduce the step from 0.1 to 0.01, so my value of y will be 0.2. Let's say I'm doing 0.2. So see, for 0.2, my answer will be, it is same 0.465. If I further reduce the steps, it will take some time to solve it. So value of y is for last entry. It will be more accurate. That's all. So it is 0.0465. Okay. So this is how we can use ODE 45. If I use ODE 23, let's see what I'm getting with 0.1. So my value of, so that is 0.0465, and there is slight difference. Okay. I guess there is something ODE 15. One five. Yeah. That is ODE 15S. We can also use and check that what does this ODE 15S gives. Okay, so we are getting something. So see, that is bit different. That is 0.04628. Okay, so this is how we can solve it. It's better to use and go for accurate ODE solver than use ODE 45. Okay. Okay, so let's move ahead with the next problem. Consider the following system of linear ordinary differential equations. Dx dt is equal to y. Dy dt is equal to minus 2x minus 3y. So what is the difference here? Here we are having ODEs, coupled ODEs. Correct? The initial conditions are x of t is equal to 0 is 1. Meaning when t is equal to 0, x is equal to 1. And when t is equal to 0, my y is equal to 3. So what is the value of x at t is equal to 10? Correct? So let's write down it. Correct. So let's say my time span is equal to, when do I want to calculate? At 10. At t is equal to 10. So let's say I'm saying it 0 to 10 in interval of 1. This is my t span. So see here there is yellow thing. So there is some message. Use of bracket is unnecessary. So we can remove it. Even if we keep it, it doesn't matter. T span is given to us. Now initial gas. Initial gas is 1 and 3. So I will write y0 for first variable x, it is 1. Initial gas, not initial condition, I'm sorry. And for second variable, that value is 3. Okay. So if I want to solve the ODE, I can write t comma y is equal to ODE 45 at the rate, let's say my name of the function is ODE only, that we will be writing. Then t span comma y0. So this will be our solution. Okay, I'm sorry. So this is, yeah. So now we need to write down the function. So here function will be slight different. So my function, what do I calculate? Dy dx is equal to name of the function ODE 45. And let's say we need t comma y. So my function dy dx is equal to, so now here there are two equations, correct? So I need to write it like first row, first column. So what is my equation? Okay, so what we can do it here, we can say my, let's say my y of 1 is equal to x and y of 2 is equal to y. So my first equation is dx dt is equal to y. So my first equation y is my y of 2. Correct. And my second equation dy dx of second row and first column, that is equal to minus 2x minus 3y. So that is minus 2 into x. X is y of 1 minus 2x minus 3 into y of 2. Okay, so I have written down my equations. So let's now run the solver and see what we are getting. Okay, there are too many arguments. Okay, here we don't need t. It's correct. Why is it showing like that? E comma. Oh, okay, okay. It is not ODE 45. Name of the solver is ODE only. Okay, so see, we are getting the solution, but what are we asked? T is equal to 10. What is the value of x? So my x is y of 1. So for y of 1, last entry, that is 2.2750 into 10 raised to minus 4. That is my answer. If I further increase the step to 5, it will be really bad result. 2 point, yeah, still this OD 45 is giving correct, but generally we should not use this long. We should have the value of delta, this difference to be as small as possible. I use 0.01. So we are getting same. So instead of seeing it like this, what I can do? I can write y of first, last row and first column. That will give me the answer. No, this is giving also last row meaning end. I need to write end. In last row, first column. So that is giving 0.0002275. Okay, so this is how we can use our ODE solver. If we use ODE 23, let's take difference of 1. I guess it's not going to affect a lot. See, same. And if we use ODE 15S, then also it is not much. It is changing after some digit. Okay, so this is how we can use ODE 45 or any ODE solver. Okay, let's move ahead with the next problem. One more problem we will be taking, that is first equation is minus 1.2y1 plus 1.5y2 and second equation is 40y1 minus 190.3y2, and initial conditions are given: x is equal to 0, y1 is equal to 1, x is equal to 0, y2 is equal to 0.1, and what is the value of y1 at x is equal to 100. So what we can do here, instead of t it is x. So let's write x span with 100. So my last entry should be from 0 to 100. And what is my initial condition? For first variable it is 1 and for second variable it is 0.1. So for first variable it is 1. For the second variable it is 0.1. Okay, here it won't change anything. I can write x comma y. Okay, I need y1 at x is equal to 100. So this is also correct. Y first, last row and first column. That will give me that. Okay, so here let's write down our equation x comma y. So my first equation is 1 minus 1.2 y1 minus 1.2 into y1. Y1 is my y of 1. So here I can write as y1 is equal to y of 1 is my y1 and y of 2 is my y2. So my first equation is minus 1.2 y of 1 plus 1.5 y of 2 plus 1.5 into y of, and my second equation is 40 into y1. So it is 40 into y1 minus 190.3 into y2. 190.3 into y2. Okay, and if I solve this, I guess here x is not required to define. Let's try to remove it and see if it works. Yeah, okay, it should be here x span, not t span, because here we have defined it as x span, not t span. So if I run this, yeah, it won't work. Here it should be x comma y. Both variables are required, dependent and independent. Okay, so the answer that I am getting is 1.0937 into 10 raised to minus 8. That is nothing but a 0. Okay, so this is how we can solve ordinary differential equations. So we learned ODE 45 solver, ODE 23, and ODE 15S solver to solve this kind of problem. Okay, let's learn small thing here. Let's say I want to plot the solution. So how can I plot it? So I can use plot x comma y, but my y is, let's say first it is all rows and first column, so that will give me y1. I can keep hold on to not close the plot, then I can keep on the same plot x comma y2. So y2 is y of all rows and second column, so that's why colon comma 2. Then let's say my x label is x, my y label, let's say it is y. Correct. I can also provide here legend stating y1 my first value and y2 my second value. I can further give title with variation. Let's say I'm writing something variation of y1 and y2 with x. So this is my title. One more thing that I can do is I can, let's say I'm giving color also I can give, let's say it is blue. Okay, no, B is black, not blue. Yeah, B is blue and K is black. I'm sorry. B is blue and K is black. I can do this. See if I run it. So see, we are having, I will open it in the new tab. So see, this is the solution. But what further we can do? We can also change the line width. So let's say line width is, let's say 1.5. Similarly here also line width is 1.5. So this is how you can change the appearance of your plot. So see, it is quite thick. So see, this is how, this is my y1 and this is my y2. Okay. So this is what we have learned about ordinary differential equations. In this ODE part, we further learn how we can plot our data. Okay. So this is all about initial value ordinary differential problem. So now let's move ahead with the next problem statements, that is ordinary differential equation with boundary value problem. So what is boundary value problem? So let's say this is your rod, and yet let's say this is x is equal to 0 and x is equal to L. So let's say your boundary condition is t at x is equal to 0 is something and t at x is equal to L is something. So this is called boundary value problem. So boundary value problems are mostly second order equations because there are two conditions. So you need two ways to solve. So it is, that's why it is a second order equation. So let's read out the problem statement and see what it is asking us to do. The problem statement says that the steady state material balance for diffusion and reaction in spherical catalyst pellet leads to the following boundary value problem, that is d square c dr square plus 2 by r dc dr is equal to phi square into c raised to n, where c is dimensionless concentration, r is dimensionless radial position, phi is Thiele modulus, n is order of reaction, and the boundary conditions are r is equal to 0, dcdr is 0, and r is equal to 1, c is equal to 1. So what kind of boundary conditions are these that we are supposed to say? So this one is a Dirichlet boundary condition. What is Dirichlet boundary condition? Let's say this is my temperature rod, T is equal to TA. X is equal to 0, T is equal to TA. So this is called Dirichlet boundary condition. But let's say at X is equal to L, let's say minus K del T del X is equal to 0. So this is called Newman boundary condition. So this R is equal to 1, C is equal to 1 is called Dirichlet boundary condition, and R is equal to 0. DCDR is also is equal to 0. That is called Newman boundary condition. Okay, so these kind of questions may be there. What is Robin mixed boundary conditions? Meaning both conditions are there, one Dirichlet and one Newman. Both conditions are there, then this kind of conditions are called Newman Robin mixed boundary condition. Correct? Okay, let's move ahead. Let's try to solve this problem. Consider the following boundary value problem solved using BBP4C solver in MATLAB. My problem statement is d square y by dx square plus dy by dx is equal to 2y, y of 0 is equal to 0 and y of 1 is equal to 1, and plot the solution. So let's first see about BBP4C. Let's try to recall about BBP4C. See. So see, this BBP4C integrates a system of differential equations of the form y prime is equal to f of x comma y specified by ODE function subject to the boundary conditions described by BC fun and initial solution gas sol init. Use the BBP init function to create the initial gas sol init. So if we first read about BBP init, so it says that sol init is equal to BBP init x comma y. So x is the initial mass and initial gas solution is y init. So if we solve this problem, so let's do it. Okay, so my x mass, what is the value of x? It is 0 to 1, right? One boundary is at x is equal to 0 and second boundary is at x is equal to 1. So let's say I'm creating 0 to 1 in interval of 0.1. So this is my x mass. Okay. So what is my sol init? Sol init is equal to BBP init. Let's write sol init is equal to BBP init. Then it is x comma y. So x I am having x mass, and for y I can write a function to guess. Let's say it's guess. We will be writing it function at the end. Okay. So I have created my BBP init. Now to solve the equation, my solution is equal to BBP4C. Solution is equal to BBP4C. Then what is it writing? ODE function. So I will be writing it at the rate ODE function. Then boundary condition function. So at the rate boundary condition BC function. Then I need sol init. Okay. Then what further do I need? Yeah, that's all we need. Okay, so let's first write down the functions. So my function, first function is ODE function. So let's say function dy dx is equal to, what is the name of the function? ODE function. ODE function x comma y. I will end it. So my first function dy dx is equal to, so how do we solve this? We solve it by saying this, that my y of 1 is equal to y and my y of 2 is equal to y prime. Okay. So my first equation is dy by dx. D square y by dx square. Correct. So d square y by dx square is nothing but y of 2. And my second part of equation is 2y minus dy by dx. So 2 into y of 1 minus dy by dx, that is y of 2. Correct. And I have already ended the function. So this is our ODE function. Now I need to write down boundary function. So let's say function boundary is equal to BC fun of two boundary conditions ya comma yb. Okay, I will have one end. So my boundary is equal to, okay. So what is my first boundary condition? Y of 0 minus 0. So ya of 1. Why ya of 1? Because it is normal value. It is at y naught at dy by dx. That's why it is ya of 1 minus 0. So minus 0 we don't need to mention it. And my second condition is y of 1 minus 1. So yb of 1 minus 1. Okay. So this is my second boundary condition. Okay. So let's move ahead and let's write down initial guess function. So function, I guess we can also skip that part. We can, instead of writing this, we can just give something, let's say 1 comma 2. And let's run it and see what we are getting. Okay, so we are getting some solution, but what is asked to us? Plot the solution. So let's plot the solution. That plot. Okay, so I need y. Sol dot y of first row. And here sol dot x. Okay, so my on x-axis it will be sol dot x. On my y-axis it is sol dot y of first row and all columns. Correct. So what further we can do? We can improve our plot with, let's say, color. I am keeping it as black, or let's say red this time. Okay. Further we can give line width. So line width is, let's say, 1.5. And X label is my X. Y label is my Y. And I can give a title to the chart. That is, let's say, variation of Y with X. Okay. So let's run it and see how our plot looks. So see. So this is how our plot looks. So how X is varying with Y. So it is nearly linear. Correct. If I further reduce my mesh size, so it is linear. So this is how we can plot our solution. Okay. So this is all about our boundary value problems. So for boundary value problems, we learned how we can use BBP 4C solver, BBP init to define initial condition, initial guess plus XMS that we can do. And we also learned about various kinds of boundary condition, Dirichlet boundary condition and Dirichlet boundary condition and human boundary condition. Okay, so this is all about ordinary differential equations. So till now what we covered, we first looked at nonlinear equations that we solved using fsolve, fzero and roots command for polynomials. Then we looked at linear equations. For that we used linsolve MATLAB inbuilt function, and if inverse of matrix is defined, then we can also use inverse of A into B, or we can use A backslash B to plot that. Further, we used ordinary differential equation initial value problem, and for that we used ODE 45, ODE 23 or ODE 15 as solver to solve the solution or to solve the problem. Now, further to solve boundary value problems, we need BBP 4C MATLAB inbuilt function with BBP init function. BBP init uses is used to define my X mass and initial gas. Okay, so this is what we have revised till now. So further we will be going for partial differential equation. So partial differential equation is, let's say I am writing Laplace equation del square t by del x square plus del square t by del y square plus del square t by. I'm sorry guys, just give me a minute. It is something important. Okay, I'm so sorry. I had to receive the call. Okay, so we were looking at partial differential equation. So this is called PDE equation where it is d square t dx square del square t del y square plus del square t del z square is equal to 0. So here t is dependent on all three variables x, y, and z. That's why it is called partial differential equation. So the question is, a long cylinder of radius r has a uniform initial temperature Ti throughout. At time t is equal to 0, the cylinder is placed in a medium of temperature T0. The unsteady state temperature distribution inside the cylinder is given by the following PDE: 1 upon alpha dt is equal to 1 upon r d dr r dt dr. Here r is the radial position, t is the time, capital T is the temperature, and alpha is the thermal diffusivity. Which one of the following gives the correct definition of PDE function for PDEP solver? So first let's have a look at PDEP solver. Okay. So for PDEP, I am searching it PDEP solver. So the solution is equal to PDEP m comma PDE function comma IC function comma BC function comma xmas comma tsman. So what is m? Okay, so for m is equal to 1 for the cylindrical coordinates. Okay, so I guess it is defined below. Yeah, here. So this is my code equation, correct? So my m is equal to 0 for Cartesian coordinates, m is equal to 1 for cylindrical coordinates, and m is equal to 2 for spherical coordinates. Okay. My value of, if I compare this equation, so coefficient of del u del t is my c, correct? And this x raised to minus m. So here if we see, here it is r raised to minus m and r raised to minus 1. So my m is equal to 1 here. C is coefficient of del u del t. So my coefficient of del t here is 1 upon alpha. So my value of c is equal to 1 upon alpha. My function f is equal to u by t. So that is nothing but this value t by r. In my s, this is additional term. We don't have any additional term here. So my s is equal to 0. So the correct option will have m is equal to 1. Then c is equal to 1 upon alpha. So this is not my answer because here c is equal to 1. So this is not the answer. Here m is equal to 0. So this is also not the answer. Correct? Then if I move ahead, so here also m is equal to 1. So yeah, this can be, here m is equal to 0. So this can't be answer. So our answer is this. M is equal to 1. My c is equal to 1 upon alpha. F is equal to dt dr and my s is equal to 0. So this kind of problem statements can be given to you in your examination and you just have to identify which is the correct way of writing the function. Okay, so let's try to solve a problem where we will be writing a function. So the problem statement says that consider the problem of unsteady state heat conduction in the x coordinate in a slab of length L for which the governing PDE is this one. Okay, I have not written down the PDE. Okay. Here rho is the density. Cp is, it is that equation d square t by dx square. Okay, I'll write it down here. Okay, I forgot to add that equation. Okay, I will do that. Let's first read the problem statement. Here rho is the density, Cp is the specific heat, and K is the thermal conductivity of the material. The initial and boundary conditions are given as T at any x, and for time t is equal to 0 is 300, and minus K del T del x is equal to Q, and T of L comma T is equal to 0. Given L is equal to 0.4, K is equal to 350 watt per meter per Kelvin, rho is equal to 5000 kg per meter cube, Cp is equal to 100 joules per kg per Kelvin, and Q is equal to 1 into 10 raised to 6 watt per meter square. At the end of 10 seconds, the value of T at x is equal to 0.2 meter is what? That we are supposed to say. So let's try to solve it using PDEP MATLAB inbuilt function. So what is the syntax for PDEP? This is the syntax. Okay, let me just correct this problem statement. We are missing some equation. So let me just add that part. Okay, yeah, this is my equation. Okay, so I will just take the picture and add that. It is Control S. Let's add it in the same folder so we don't have to search it here only. So my equation is this one. Okay, so this is the equation. Okay, rho Cp del T is equal to K del square T del X square. Correct? So I'm sorry for this part missing out. Okay, so my solution is equal to PDP. Let's copy this. Okay, I can't copy it, so I will have to write. So let's first. Okay, so my solution is sol is equal to PDP of M, comma, see here also it's available, PDE function, then initial condition function, then boundary condition function, then xmax and tspan. Okay, this is what we require. Okay, so let's try to give what is the value of m here. M is equal to 0, correct? Because there is no, if we compare it with this thing, it is obvious that it is Cartesian coordinate. There is no x raised to minus m term here. There is no x raised to minus m term here. So that is m is equal to 0. Our first criteria. Then x mass. We can give some value of x mass as we are supposed to find at x is equal to 0.2. Correct? X is equal to 0.2. So let's do it from 0 to 0.01 to 0.2 x mass. My time span t span is equal to, I need to calculate it at, it is not given to us, right? Time is not given. So let's take some random value of time from, let's say, 0 to 0.1 to 10. Okay, let's keep gap of 1 instead of 0.1. So t span is also defined. Okay, these two parts we have defined, and now the left three parts are functions. So I need to add one thing, one important thing, at the rate sign, because we are writing function at below. So we need at the rate sign. Okay, so my first function, how can I define the function? Let's have a look at here. So my first function is function CFS, function C comma F comma S is equal to, my name of the function is PD fun that we have written here. So we'll keep that only. Now I need to give the data X, then T, X, then small time, then temperature, and my equation dt dx and n. So from here, what is the value of C, F, and S? Okay, so if we compare our equation C is coefficient of this term. So what is the coefficient? Rho into Cp divided by K. Let's write it like that. Rho Cp by K. So it is rho into Cp divided by K. So I need to define value of rho. So what is the value of rho given in the problem? Value of rho is 5000 kg per meter cube. Then value of Cp is equal to 100 joules per kg Kelvin. Rho, Cp and K. Value of K thermal conductivity is 0.4. Okay. So this is my first term C and my second term F. As I have already taken K below, so my F is just dt dx. If you are not doing that, then you can write K into dt dx. Okay. The way you want to write, it's not going to affect anything. So my that term is dt dx. Okay, and my s, there is no plus additional term, so it is 0. Okay, so this is my first function of PDE fun. Now I need to define initial function. So function. So what does initial condition function will give? That is defined as u0. So let's say, so let's write here function t0 is equal to what is the name of that function? IC function, IC fun. And what do I need? I just need x. And so what is that value? T0 is equal to, what is that number? That is 300. So I just need to write T0 equal to 300. Okay. Now I will define boundary condition. So for defining boundary condition, we need this form PLQL, P meaning my normal Dirichlet condition, and Q meaning my this condition, Newman condition. So function PLQL, PRQR. Okay, let's copy this from here only. So this function PLQL, PRQR is equal to, what is the name of my function? It is BC fun. So it is boundary condition function XL. Let's say it is TL, XR, TR, and my time. And so my here, what is my P left? My left boundary condition at x is equal to 0. It is Dirichlet. It is not. It is Newman. It is not Dirichlet. So my PL will be equal to 0. So I will have some value of QL. So QL is just defined as this coefficient of this dt dx term. So that is minus k by q. So it is minus k divided by q. So one task is I need to define the value of k and q. So my value of k is equal to k is equal to 350 and my q is equal to 1e6. So 1 into 10 raised to 6, right? 1e6. So PLQL is there and my PR is equal to, what is the value of my PR? PR is T minus 0. So it is nothing but TR. TR minus 0. So that is TR. And there is no Newman condition. So QR also is equal to 0. Okay. So here we have defined our all boundary conditions. So what are we asked? We are asked, okay, I will close this. So we are asked to, okay, t is equal to 10 second is given here. Okay. So what is the value of x at point 2? So let's first run this. So I have solution. So at last time and last column. So that will be my answer. So it is simply solution of last row and all columns that will give me the answer. So that is coming out to be 0 only. Okay, so my correct answer is, oh no, sorry, it's not 0. I'm sorry, it is 300. No, not 300. It is 277. Okay, so the nearest integer is 275. Okay, so my correct answer is 275. So here we learned PDE function, how to write that, then initial condition function and boundary condition function. Most important thing to remember, m is equal to 0 for Cartesian coordinates, m is equal to 1 for cylindrical coordinates, and m is equal to 2 for spherical coordinates. C is the coefficient of my time evolution differential. Let's say del t, del x, del t, coefficient of that term is C. S is some additional term. Let's say I'm writing k del t is equal to del square t del x square plus m. So that plus term is taken care by S part. Okay, so this is how we can solve partial differential equation. Let's move ahead. So for this, which kind of equations are these that we have to say? So for this first equation, if I write the coefficient matrix, so del square del t, del square t del x square coefficient is 1. There is no del square t del x del y, so it is 0. Here also there is no del square t del y del x 0, and this term is del square t del y square 1. So if I find the eigenvalue of this, so what will be the eigenvalue of this? If I directly calculate from MATLAB, so if my A is equal to 1 0 0 1, so my eigenvalue of A is I am getting 1. Okay. So if my eigenvalues are, both eigenvalues are all of same sign, so it is positive 1 comma 1. When my eigenvalues are of same sign, then it is called elliptic PD. Okay. For the second equation, my first coefficient of this term, let's say this value is 1 and 1 and 0. And for this value, if I keep this side, so it is 0 comma minus 1. Okay. So my eigenvalues will be different, right? 1 0 0 minus 1. 1 0 0 minus 1. And if I find the eigenvalue, it is minus 1 1. So it is combination of positive and negative values. And when there is this case of combination of positive and negative, then it is called a hyperbolic PD. There is one more kind, that is parabolic. So for parabolic, at least one eigenvalue should be 0. So here my correct answer will be answer C. Elliptic, A is elliptic and my B is hyperbolic. Okay, so these kind of questions can be there in your examination. Now let's move ahead with the next statement. Okay, so this is all about PDE function. So we learned about PDEP, MATLAB inbuilt solver with various values of M, how we can define all those things that we have learned. Okay, so let's move ahead with the next part, that is PDEToolbox. So let's first try to, I guess this question is not going to be there in our examination, but let's try to solve this thing as practice. So if I open my PDEToolbox, so I need to go to apps. And from here, I need to choose PDE modeler. Okay, so let's read out the problem statement first. What it says, the problem statement says that a metal plate 1 meter cross 1 meter is placed such that its four edges are kept at different temperatures as shown in the figure. The steady state temperature distribution in the plate is given by the Laplace equation, that is del square t del x square plus del square t del y square is equal to 0. And we are supposed to find the correct temperature distribution in the plate. Okay, so for this, let's solve this. So first we need to change the system. We are dealing with heat transfer. So here I will choose heat transfer. Then I will go to draw option. I will go to draw mode. I will, let's say I'm selecting some rectangle. So I will be drawing it. So let's see, I have drawn it, but it is something random. So it is 0 1 to 0 1. Okay, so I can change the coordinates of this. Let's say my left is 0 0 0 1 1 1. Okay, so it is 0 to 1 0 to 1. Further, what I can edit, I can edit my axis limits. I can, because this area is not required for us. So what I can do, I can keep from minus 0.5 to 1.5, and here also y-axis minus 0.5 to 1.5. I can apply it. Okay, so this is how my problem, my statement look like. Now I need to give boundary conditions. So what I will do, I will go to boundary action section and I will click on boundary mode. So now boundary mode is enabled. So for this first boundary lowermost, my temperature is 20. So I will click here. So see, I will click here and I will write the value of temperature as 20 and I will press OK. Then similarly for this, okay, let's write this down later. For this it is 30 and for this it is 40. So I will choose this one. I will write my temperature as 30. Okay. And similarly for this portion, I will write down it as 40. Okay. For now this part, dt dy is equal to 0 is given. So what I will go to Newman part. So I will write my heat flux is equal to 0. So it will take care of that. dt dy is equal to 0. I'll just press OK. Okay. So my problem is now ready. Now I need to create mesh. So I will go to mesh mode. Okay. So mesh will be created. So see, you can see here it's not finite difference. Finite difference. What is finite difference? So let's say at equal interval, let's say 0.1, 0.2, 0.3. Like that, all meshes are created. It's not finite difference. Here it is finite element. Here it is creating triangular elements in mesh. Further, what I can do, I can define this mesh for more accurate prediction. Okay. Now I will solve this. So I will click on solve PDE. So see, my this lower end, my temperature was 20. So that is represented by this color. This end, it was 30. This end, it was 40. And here this end, my del T del Y is equal to 0. So my sum temperature is del T del Y is equal to 0. Yeah. Okay. So this is my solution. So this is how we can deal with PDE toolbox. This is not going to be there in your examination most probably, but just for sake of doing it or just for sake of showing it, I am doing that. So if we move ahead, the question is the PDE toolbox in MATLAB uses blank for solution of several types of PDs. So this we just discussed. So that is finite volume method, not finite difference method. Sorry, I'm really sorry, not finite volume, it is finite element. We created element of, let's say, triangular, square, like that. So it is finite element method for PDE toolbox. Okay, my next statement is, which of the following is the condition? Which of the following is the condition for the second order partial differential equation to be hyperbolic? So for hyperbolic, the condition is my b square minus ac should be greater than 0. This is the condition for hyperbolic. So you guys should remember these things. So for b square minus ac greater than 0. Guys, let me just check this once again. I guess I hope I have not made any mistake. Oh, not 9, 10. It's 10. Yeah, hyperbolic b square minus ac is greater than 0. Okay, it is correct. Okay. Okay, next problem. Yeah, this kind of problems can be there in your exam. For what value of x and y will the following PDE be hyperbolic? So my standard equation is A del square u del x square plus 2 into B del square u by del x del y plus C del square u by del y square is equal to 0. So my A is equal to 1 plus y. My 2b is equal to minus 2, 1 minus x. Therefore, my b is equal to minus of 1 minus x. So x minus 1 and my c is equal to minus of 1 minus y, so that is nothing but y minus 1. Okay, so my condition for hyperbolic is b square minus ac is greater than 0. So my b square is x minus 1 whole square minus ac y plus 1 y minus 1 greater than 0. So x minus 1 whole square minus y square minus 1. So minus y plus 1 should be greater than 0. Okay, if I put x is equal to 0 and y is equal to 1. So here x is equal to 0. So it is 1. Y is equal to 1. So minus 1 plus 1. So it is 1 is greater than 0. So my first part is at least this one. If I put x is equal to 1, y is equal to 0. So x is equal to 1, 1 minus 1 whole square is 0. Y is minus 1 plus 1. So that is 0. So this is not the case. Then x is equal to 2, y is equal to 1. X is equal to 2, 2 minus 1 whole square is 1. Minus 2 square is 4 plus 1. So 1 plus 1, 2 minus 4. So this is negative. And y is equal, x is equal to 1, y is equal to 2. So x is equal to, oh guys, I made a mistake. Let's again see option C. Option C is 2 comma 1. So 2 minus 1 whole square 1 minus 1 plus 1 greater than 0. So this is also the solution. And here x is equal to 1, y is equal to 2. So 1 minus 1 0 minus 2 square plus 1. So greater than 0? No, this is not greater than 0. So we have two solutions. There can be many solutions. But from the options, we have two solutions available for hyperbolic kind of PDE. For elliptic, I guess it is less than 0. Okay, so this is all about PDE toolbox. So we learned, we revised how we can use this thing. So now let's further move ahead with the optimization part. So optimization, the first problem is locate the minimum point of this function f of x is equal to x1 square plus x2 minus 11 whole square plus x2 square plus x1 minus 7 whole square, starting at the initial point x0 as minus 5 using the MATLAB function fminsearch. Use the optim set options to set the optimization options to display all iterations and set function tolerance as 10 is to minus 8. So let's go to MATLAB search help desk and see what is fmin search. So if I go to this help desk, I will find fmin search. So see this fmin search. So x is equal to fmin search f comma x0. Okay, and there are options. So if we want to use these options, so we need to go for optim set. So let's first create fmin search. Let's first set up that part. So I will use clear all, close all those things. Correct. Now I will define my function f is equal to at the rate of x. My function is x1 square plus x2 minus 11 whole square. So x of 1 square, x1 square plus x2 plus x of 2 minus 11 whole square plus x2 square, x of 2 square plus x1 minus 7 whole square. That is also squared, right? That is also whole square. Okay. So that is also whole square. Now, what is the syntax for fmin search? My fmin search x comma f value, x comma f value is equal to fmin search, then It is function x0 options. So my function is f x0 and options. So let's first define x0, that is -5 minus 5. Okay, so I will write down. Okay, and for options part, we checked we need to use optim set of till. So let's search about optim set. So how can we define optim set? So we need to write some what we want to do. And this tolerance part is only important. And we also need to show the iterations. So what we'll do first, we'll write display. Okay, what do we want to display? We want to display iterations. So that is by iter. Then we are defining tolerance function. And what is the value that we are told in the problem statement? We are told as 10 is to minus 8. So that is 1e minus 8. Okay. And if I solve this, view, here it should, yeah, I will get the solution. Optim set, optim set. Okay. Yeah. Optim set. Spelling was wrong. Okay. So see, each iteration is shown. And what is my function value? Okay. It's not shown. Yeah, it is shown. Okay. Optimization is terminated here. Why? X1 square plus x2 minus 11 whole square plus x2 square plus x1 minus 7 whole square. This is correct. Minus 5 is my initial guess. Yeah, it should have worked. This is strange. Yeah, this value minus 3.77, meaning minus 3.78 and minus 3.28. So this is our correct answer. Okay. Next question is, consider the following optimization problem. Minimize of x with 100 into x2 minus x1 square whole square plus 1 minus x1 whole square. This I need to minimize with some constraint. X1 plus 2x2 is less than equal to 4. 2x1 plus x2 is equal to 1. 0 less than equal to x1 less than equal to 0.4 and 0 less than equal to x2 less than equal to 0.4. Initial guess is given as 1, 1. And we need to use fmincon. Fmincon is used for constraint optimization. So I will write fmincon. Let's search. This one is bit tricky to use. So see, this is the format. So let's do one thing. Let's first write down the equation. Okay, what is my equation? Let's first write down the equation and go step by step. 100 into x2 minus x1 square whole square. 100 into x2 x of 2 minus x1 square that whole square. Okay, this is my first term plus 1 minus x1 whole square plus 1 minus x of 1 whole square. So now this is my syntax. So let's write syntax first and then try to understand what part what is. X is equal to fmincon. What is the syntax? Function x0 ab. It is function x0 a b. Then it is aeq beq, lower bound, upper bound, and non-lincoln. aeq beq, then lower bound, upper bound, and let's say I'm giving the name of that as constraint. Okay, so let's first understand. Okay, not function here, it's f. Okay, so let's first understand what are these terms. So if we go to description part, my c of x is less than equal to 0. Do we have something like that? C of x is less than equal to 0. This first term, x1 plus 2x2 minus 4 is less than equal to 0. So that is first. So we have value of c. Then c into equation of x is equal to 0. So this term also we have 2x1 plus 2x2, 2x1 plus x2 minus 1 is equal to 0. So CEQ term is also there. AX less than equal to B, that we don't have. So our A and B are null matrix. Same AQ into X is equal to BQ, that is also not there. So that AQ, BQ will also be null terms. And this lower bound and upper bound is given as 0, 0 and zero point 0.4, 0.4. Okay, so let's implement that. So my A is equal to null matrix. B also is equal to null matrix. Then AEQ is equal to null matrix. BEQ also is equal to null matrix. Okay, these terms we have taken care. Okay, lower bound I need to write. So what is lower bound? For first variable x1 it is 0. For second variable x2 it is 0. So 0 comma 0. For upper bound, for first variable it is 0.4. For second variable it is 0.4. So 0.4, 0.4. Okay, and I have defined my equation. Okay, so now I need to write down this constraint function. So what do we need from constraint function? We need C and CEQ. So I will write it down as function. What will I get? C comma CEQ is equal to constraints in X. Correct? And I will press one and. So my C is equal to first equation, this one, x1 plus 2x2 minus 4. So x of 1 plus 2 into x of 2 minus 4. And my second constraint is CEQ is equal to 2x1 plus x2 minus 1. 2 into x of 1 plus x of 2 minus 1. Okay, this is my second. So if I run this, I should get my solution. X0 is unknown. Yeah, we have not defined initially. Guess. So what is stored? 1, 1 transpose. So my x0 is equal to 1, comma 1. Okay, let's run it and see what we are getting. Constraints. Here what I have written, I guess names are different. Okay, here spelling is wrong. Now it's correct. If I run it. Okay, so we have found a solution that is 0.399, meaning 0.4 and 0.2. So 0.4 and 0.2 is my solution. So this is all about optimization part. So for optimization, we learned about fminsearch and fmincon option. Okay, so now let's move ahead with the last part of data fitting. This is really easy part to do, but very useful For those, at least those who are doing PhD with experiments or simulations, this part will be mostly useful. Okay, so this data fitting part. So you are given some data. A calibration plot is to be prepared for the concentration analysis of nitrobenzene in a UV visible spectrophotometer. The concentration versus absorbance data at 260 nanometer wavelength are given in the following table. Use polyfit to fit the equation as absorbance is equal to AC plus B. So my absorbance is equal to A into C plus B. So I need to find A and B and determine the value of A. Okay, so we are supposed to use polyfit. So let's search about that. Why is it not showing? Okay, it is polyfit. I have written something wrong. That's why. So for polyfit, the syntax is P is equal to polyfit x comma y comma n. So x is on x-axis, whatever I want to keep. Y is on y-axis, whatever I want to fit. And n is order. Not order, they call it degree. Degree of polynomial. So here degree is 1, c raised to 1. So it is n is equal to 1. So let's try to solve this. So first I will write my absorbance. Okay, let's first write what is on x-axis is concentration C. So C is equal to, so see here it is from 0, 5, 10 like that. So I can write 0 to 35 in interval of 5. And my absorbance is equal to, okay, let's write down these values. 0, 0 0.3, 0, 0 0.3, 0 0.6, 1, 1.3, 1.6, 1.9, 1.3, 1.6, 1.9, and 2.3. Okay, so I will use x is equal to polyfit s is equal to polyfit. Okay, what is on x-axis? X-axis is having C. Y-axis is having absorbance. And I want to fit first order polynomial. Okay. So if I do this, ooh, why am I writing it again and again wrong? POLY, polyfit. So see, I am getting coefficient of 1 as 0.065. And this is my A value and my B value is minus 0.0166. Okay, so this is how you can solve. Let's see if I am solving for second order polynomial. Let's see what we are getting. So for second order polynomial, I have A, B, and C again here. So this is how you can plot it. Okay, so let's move ahead with the next problem. In a set of convective heat transfer experiments for turbulent flow through a pipe, data are generated for Reynolds number, Prandtl number, and Nusselt numbers as shown in the following table. It is desired to feed the data by a function of the form Nusselt number is equal to A, Reynolds number is to B, Prandtl number is to C. So here it's not polynomial, it is something different. So for this kind of problem, what do we use? We use lsqcurvefit. So using this kind of lsqcurvefit, we can do nonlinear fitting. Okay, so let's just take this example and let's try to solve this. So let's first enter all the data. That is a bit tedious task. First value is Reynolds number is equal to 11500, then 1300, 13,000, Then it is 15,000. I'm sorry, 15,000. Then 17,800. 17,800. Then next value is 21,300. 21,300. Then 22,700. 22,700. And my last number is 25,600. I will write down my parental number, that is 3.5, 18.9, 3.5, 18.9, 35.4, 56.7, 35.4, 56.7, 89.1, 95.2. My last data is 112.3. Okay, this is parental number. Now let's move it with Nusselt number. So Nusselt number is equal to 68.3, 68.3, then 146.7, 146.7, then 209.1, 209.1, then 289.7, 289.7, then 403.1, 403.1, 434.5, 5, and last value is 511.1. Okay, so now I need to define the model that I want to feed. So model is equal to, let's say I am writing C as my coefficient, C comma X meaning my data. Okay, so what is my equation? C of 1, A is my C of 1. So C of 1 into RE raised to B. So RE, I can't write RE. So I have to write X of first row, all columns, raised to B into parental number is to C. Yeah, into parental number. So X of, comma, this is to C. Okay, here we need to put one dot because it is matrix. Okay, so I have written down the model. Now I need to give some initial guess. So okay, I can't write here C. Okay, B is my, I can't write B. B is my C of 2 and C is my C of. Set is 0, 0, 0. Okay, now I need to find coefficient. So my coefficient C is equal to lsqcurvefit. Then the syntax is, first I need down my model or function that I want to feed. Then my second thing is C0 value that I have to write. Then what is my x-axis? Reynolds number. First one is x data 1 is my Reynolds number and my x data 2 is parental number and my y that I want to feed is Nusselt number. Okay, if I do this, if I solve this, I will have coefficients. So I am getting my coefficient as, wait, let me open it here. So see, this is A, B, and C. So we are asked to say the value of B. So that is 0.81 A. Okay, so this is all about curve fitting. So that's all for this. So let's have one overview. So first we solve nonlinear kind of equation, and for that we used fsolve, fzero, and roots inbuilt command. Then further we solved linear equations, and for that we used linsolve command or inverse of A into B or A backslash B. Then Further, we solved ODE, ordinary differential equation, initial value problem. For that, we used ODE 45 solver, ODE 23, and ODE 15S solver. Further, for ordinary differential equation, boundary value problem, we used BVP4C, MATLAB inbuilt function, and BVP init to define my X mass and initial guess. Then we solved partial differential equation. For that, we used PDEpe toolbox to solve that. Further, what did we do? We used PDEToolbox and we checked one problem. Then for the seventh part, we did optimization, and for optimization, we solved fminsearch and fmincon. Fmincon is basically for constraint optimization. Further down, we looked at curve fitting. So when we are willing to fit a polynomial, then we can directly use polyfit MATLAB function. Or if it is some nonlinear equation, then I can use lsqcurvefit. So we learned everything that sir has covered in his lectures. So this is all from my side for this whole course. Thank you so much. And this is my email ID. If someone is having any query or someone wants to ask something regarding academics, regarding some studies, regarding some other subjects or some doubts, please feel free to write me an email. I will get back to you as early as possible. So thank you so much and all the very best. Thank you so much.